Okay, good evening, dear students. Today we are going to begin the topic linear vector spaces, right? Before entering deep into the topic, you need to have few preliminary concepts. So let's have a look on those, right? Okay, you people do have a fair idea on sets, I hope. Set is nothing but a group of elements sharing the same properties. So now let's see what a binary operation on a set is, right? So binary operation on a set, say we have a set X, okay? So what does binary operation on a set mean? It is given by, just a second. This is how we define a binary operation, right? That means if we perform the operation on two members of the same set X, we get a third member which also belongs to the same set. So the operation which on performing on the members of the set gives me another member which also belongs to the same set, that operation is called a binary operation, right? So I can cite a very simple example. Say we considered the set of integers, right? And addition on integers is defined by obviously m equal to n, you know that. So this is a binary operation on set, on integers, binary operation on z, right? Because on adding to integers you will always get an integer. So addition is a binary operation on integers, right? Similarly, even multiplication is also a binary operation on integers, the set integer, right? But if you think of division is not a binary operation on the set of integers, right? Because the result obtained might not be an element of the integer set, right? So division is not a binary operation on integers, but multiplication and addition are. Okay, so this is what a binary operation means. Now let's try to understand what a group is, right? A group is a set G of elements with a binary operation written Y such that belong to. Okay, so I would before writing the axioms, I would like to tell you group is a set of anything. It needs to contain any element and a binary operator or a binary operation which follows the axioms. Anything that follows these axioms will be called as a group, right? Now what the axioms are, say for example we have the elements from a group x, y, z, they are associative, right? The elements of a group needs to be associative. Secondly, G contains an identity element. One is just the notation, okay? One does not mean numerically one. The identity element can be anything, but the notation is like this. So G contains an identity element such that any element of the group, say X, binary operation 1 is equal to identity element performing the binary operation on x1 is equal to x. That means when we take the identity element of the group and any other element, and we perform the binary operation on both the elements, we get the initial element, right? That means x dot 1 is equal to 1 dot x is equal to x. If the binary operation associated with a group is plus, then over here we will have plus. So this does not necessarily mean multiplication. This means two elements, that is the identity element and the and any other element of the group, when they are associated by the the binary operation is performed on those two elements, we get the original element, right? So a group needs to follow the associative, the elements of the group needs to follow the associative law. There needs to be an identity element which is constant for the group. That means one identity element has to be there in a group which follows this rule. And the third axiom is, if x belongs to G, then there exists y belonging to G such that xy is equal to 1, right? This is called, that means we will have another element when x and that element corresponding to every x, we will have another element y such that when they are when the binary operation is performed on both of them, we get the identity element, right? And this y is called the right inverse of x, right inverse of x. So these three are the axioms. For anything to be called as a group, there needs to be a set of elements and a binary operation associated such that on performing the binary operations on the elements of the group, it is associative. There needs to be a particular identity element of the group. It is unique for the group, which on operating the binary operation needs to be done, which on operating on any other element of the group gives us only that element back. And thirdly, every element should have another right inverse element. That means when the binary operation is performed on both the elements, we will get the identity element back, right? Now I'll cite a simple example so that these axioms get clear. Okay, say for example the set of integers z form a group under addition. Prove that the integers form a group under addition. So like I have already said, a group needs to have elements and a binary operation. So these two things need to be defined, right? Now we just need to check these axioms, right? Now addition, the binary operation given here is addition. We know that if we add integers, it is obviously associative, right? This need not be proved anymore. So addition is associative, and we know that. Because 1 plus 2 plus 3 is obviously is equal to 1 plus 2 plus 3. I mean, this is very obvious, just still if you have a problem understanding. So we know addition in integers is associative, right? So nothing needs to be proved. The second, we have to prove that G contains an identity element such that that identity element let x belong to z, right? So x and the binary operation is now plus x plus what gives me x? Obviously x plus 0 gives me x, right? Also 0 plus x gives me a x. That means any element and the identity element connected by the binary operation gives me the original element. That means 0 is the additive identity. See, the second axiom gets proved. That means I have to have an additive identity such that whenever the binary operation is performed between the identity and any element, we get back the original element, right? So 0 is the additive identity in case of integer z. So the second axiom gets fulfilled. Now I have to see there exists an inverse such that, so the third is for any x belonging to z, x plus obviously a minus x gives me 0, right? So what needs to be fulfilled is x binary operation performing with another element has to give me the identity element, right? So minus x plus a minus x will give me a 0, and minus x also belongs to the set of integers. So our third axiom also gets fulfilled, that is right inverse exists. That means the integers form a group under addition. So whenever you are asked this kind of asked to prove that something forms a group or not, you need to show that whether these axioms are satisfied or not, right? Now, what do you understand by a abelian group? Abelian group. Okay, abelian group is a group. That means all the previous three axioms needs to be fulfilled. In addition to that, an abelian group will be commutative, right? That means x binary operation y is equal to y binary operation x. If this gets followed in addition to the axioms of all the present three axioms of group, then that is termed as an abelian group, right? Now it's a homework to show that the set 1, minus 1 is an abelian group under multiplication, right? It's an abelian group under multiplication. It's very easy. It's just that you have to write the 4 axioms and they easily get proved. So do this as a homework, okay? Now we have to see a few basic properties of groups. Now let's look at the basic properties of groups, okay? Properties of groups. Firstly, like I have said, every group has exactly one identity element. Identity element is unique in a group. It does not change. There is exactly one identity element in the group, right? Second property is, we have already seen every member of the group has a right inverse, that is xy is equal to 1. Now the right inverse is also equal to the left inverse. That means xy is equal to yx is equal to 1. So even if it is a non-abelian group, the right inverse will be equal to the left inverse, right? That means for every element x belonging to G, a two-sided inverse exists. A two-sided inverse exists. For all x belonging to a group, a two-sided inverse exists, okay? And the third property is the two-sided inverse is unique. The two-sided inverse is unique. That means not that there will be numerous two-sided inverse, there will be exactly one two-sided inverse to each element. Each element will have one two-sided inverse which is unique from the others, okay? So now let's try to prove these. First is, every group has exactly one identity element, that is uniqueness uniqueness of identity. Now the rule to these kind of proofs are, we will consider there are two identities and then we will show both the identities are the same. Okay, so let's consider, let 1 and 1 prime be the two identities of a group G, right? So, and let the binary operation, we are just considering the binary operation is given by b dot x y is equal to xy. Say the binary operation is dot, we are just writing it like this. Okay, it can be a plus, minus or whatever for various groups, but for our convenience we are writing it like this. Okay, so we'll start with the 1. This 1 is an element, right? And we have said 1 prime is also the identity element, right? So whenever we over here we are using the word multiplication, we are considering binary operations multiplication. Whenever we are multiplying any element with the identity element, we'll get the same 1. So 1 can be written as 1 dot 1 prime, because we have considered 1 prime to be the identity element, right? Which is equal to 1 prime again, because we have also written 1 is also the identity element, right? That means 1 we have written first 1 is we have considered 1 to be an element and 1 prime to be the identity element, so I have multiplied both of this. But since we have also considered 1 to be the identity element, this can be written as 1 prime. So finally what we get is 1 is equal to 1 prime. That means there cannot be two identity elements in a group. Both of them have finally come out to be equal, right? Now let's go to the second proof. Second is two-sided inverse exists. That means we have to prove left inverse is equal to right inverse, right? What we need to prove is xy is equal to yx is equal to 1. This is what we want to prove. Okay, so let's consider, let y be the right inverse of x. That means xy is equal to 1, right? Let say z be the right inverse of y. That means yz is equal to 1. You have considered these two. Now what we need to prove, if we can prove x is equal to z, then only our motto will be served, right? If we can prove x and z are equal, that means the right-handed inverse will be equal to left inverse, right? So let's start with, say, you can start with anything for your convenience. Say I'm starting with x, right? X. Now x can be written as x dot 1, right? Since 1 is the identity element. X is equal to x dot 1, since 1 is the identity element. It is very important that in each step you write how you're performing that step, what is the reason, right? So now you can write x dot, in place of y you can write 1, you can write yz, because just now we have written yz is equal to, just a second. Okay, we have just written yz equal to 1, so we will substitute yz in place of 1, right? So yz, since yz is equal to 1. Now, like we know the elements of a group follow the associative law, so we can write xy and a z by associative law. And again, initially we have considered xy equal to 1, so y dot z, since xy is equal to 1, and this finally gives me x equal to z, since 1 is the identity. So we have already proved that xy equal to yx is equal to 1, which we intended to prove on putting back to equation a and b, right? So these proofs are very simple, just that we are not used to this kind of notation. So initial days you might find it a bit uncommon, but these are very easy in general. Okay, now the third proof is your homework. That means you have to prove that the two-sided inverse is unique. The two-sided inverse is unique. It is just a two-line proof. I am giving you the hint how to do it. You will consider that the you will consider two different two-sided inverse. That means, say we have an element xy, we have elements this belonging to a group, and we are considering x has two-sided inverse, y and z. That means xy is equal to yx is equal to 1, and the second is xz is equal to zx is equal to 1. So you will consider that x has two different two-sided inverse, and then what you will need to prove is y is equal to z. If you can prove this, then only you're having the solution, right? So start with y, use the identities, and then you can very easily reach to y equal to z. It's very easy. Okay, so this is your homework. Okay, now one more important proof. Question: prove that for all x comma y belonging to a group, xy inverse is equal to y inverse x inverse. Please practice problems like this wherever you get. Okay, so we are asked to prove this, right? Now we know xy inverse xy is equal to 1, right? Where 1 is the identity, we are considering 1 is the identity element, and we know inverse into the element gives me 1. So this is known, right? Now if we can prove, okay, so this is a known thing, right? You can understand this because the group axiom tells that inverse binary operation, the element gives me the identity. So if xy is the element, then xy inverse is the inverse of xy, and performing the binary operation we can get 1. So we know this from the axioms, right? Now we will start with, so what is our goal? How can we prove this? If we can prove that y bar x bar xy is equal to 1, if we can prove this, we can equate these two equations and finally say xy whole bar is equal to y bar x bar, right? So we'll start from this equation and try to reach over here, right? So what we will do is y bar xy is equal to y bar x bar xy. This is by associative law. Associative is equal to y bar. Now this is nothing but 1 because we have x inverse, binary operation x, and when inverse and the element acts, we obviously get the identity element. So is equal to y inverse y. Again, this is nothing. Please write the reasons why you are writing this. Again, this is nothing but the inverse operation. This will finally give me 1. That means x inverse xy is equal to 1. So now if we compare equation 1 and equation 2, we can conclude xy inverse is equal to y inverse x inverse, right? So this is all about groups. These are very abstract concepts, so you need to so you might take a bit of time to finally grab these concepts. So try to read books as much as you can, and in our next class we will start to discuss about more topics, fields, and linear vector spaces, right? So thank you.